I'm a bit afraid of what's going to happen now, based on my experience with Deutsch's algorithm and the Bernstein-Fazzirani algorithm. I hope I'm not going to spend another hour on these now, but let's see. Simon's problem. I fear that's going to be more complicated, but it seems to build up, I think, if I remember well, also on the same kind of concept and idea like the two other ones that I've been working on. So the computational complexity theory and Simon's problem is a computational problem that can be solved exponentially fast on a quantum computer. That's good. It's a little practical value, but it can be proof that quantum computing can solve this exponentially faster. What else it says here? Someone's argument was okay. So it's an inspiration for Shor's algorithm. Both problems are special cases of the abelian hidden subgroup problems, which is known to have efficient quantum algorithms. Problem description. So here's where I usually fail. That's where I failed in the last time. So the last two times to kind of fully and correctly grasp that, which led to an hour-long discussion or me trying to understand stuff. Yeah, that's again one of those oracle things here. Given a function such that promise to satisfy the property that for some s, so again with the s in here, we have for all x, y, okay, if and only if this is the, so this belongs to either all zeros or s. Okay, so okay, so if I read this correctly, it means that there are two values. So there's one string s, one binary string s, that is the result of, yeah, so basically that for all the values of x and y, which are also an n-long string, a binary string, so that the outcome of the function is the same, or 0. So in the case s equals the 0 string, then f is required to have a 1-to-1 function. Otherwise, it is a 2-to-1 function. That is, two inputs mapped to the same output. If and only if x equals y. Okay. So in other words, it's a function. F is a function such that oh yeah, that definitely helps to reformulate the problem. So, and I guess that's the sum modulo 2, because it's the same notation used in the Bernstein-Vezzerani algorithm or page in the Wikipedia. So x and x plus s are equal. And I guess that's okay. And I guess that's what inspired the thing with Shor. That's kind of like that s is the period in this case. You see, that's something I wouldn't have. That's definitely something, an insight that I didn't probably see in the first in my first videos on Simon's problem. Maybe yes, I don't remember. Should have watched them probably before starting to record this video. But okay, so yeah, basically there's a period. Okay. So the whole thing here is okay. So there's okay, and the problem is to find s. Yeah, but isn't that then period finding? Isn't that really what is this about? Find s is find the period, right? For example, if n equals 3, then the following function is an example of a function that satisfies the required and just mentioned property. So these are all the inputs, and then here you've got the, okay, this, and here you, and this is the, so 1, 2, 3, 4, 5, 6, 7. So the period is 7 in this case, is it? Oh, 6. Well, yeah. It's a binary string 6. S is 6. Okay. because if I take 1, 1, 0, 1 plus 6 in binary, right? What does this give me? 0, 1, 1? Eh. No, what am I? Oh no, sorry. That's not what it says. I don't know if you're hearing the background noises, but it's a pretty loud day today. Sorry, it's x. If so, the x is 0, 0, 0, and I add basically 6, and I get 6. So yeah, so basically f of these and f of these is the same. Yeah. Let's just get rid of everything. Okay, so it's period finding. In the case, it can easily be verified that every output of f occurs twice, and that the two input strings corresponding to any one given output have, and that the two input strings corresponding to any one given output have bitwise XOR equals S110. For example, oh, that's bitwise XOR. Yeah. Note that in this example, the function f is indeed a 2-to-1 function. Problem hardness. Intuitively, this is a very hard problem to solve in a classical way. Even if one uses randomness and accepts a small probability error, the intuition behind the hardness is reasonably simple. If you want to solve the problem classically, you need to find two different inputs, x and y, for which the value is the same. There is not necessarily any structure in the solution, f, that would help us to find two such inputs. More specifically, we can discover something about f, or what it does, only when, for two different inputs, we obtain the same output. In any case, we will need to guess different outputs before being likely to find a pair on which f takes the same output as per the birthday problem. Overview of Simon's algorithm. Okay, so let's take a look at the algorithm and see if we can sort of explain it intuitively. But I mean, it's maybe not generally period finding, but it's actually there's just one repetition, and that's what you want to. That's kind of, it's a bit more restricted than the general period finding problem. But that makes sense that it inspired Shor's algorithm. So the high-level idea behind Simon's algorithm is to probe or sample a quantum circuit enough times to find n-1 n-bit strings, that is beep, 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 such that the following equations are satisfied. Okay, that equals 0, where y times s is the modulo 2 dot product, that is this. So this linear system contains n-1 linear equations in n unknowns. Then s, now the s is fixed for a given function f. Also, note that we may not find a unique solution. Simon's quantum circuit. Quantum circuit is the implementation. A quantum state of all zero. Okay, so a quantum state of all zeros is first prepared. Half of the state is then transformed. Half of the state is then transformed using a Hadamard transform. The result is then fed into an oracle, which knows how to compute f. After that, part of the output produced by the oracle is transformed using another Hadamard transform. Finally, a measurement on the overall resulting quantum state is performed. Okay. Simon's algorithm can be thought of as an iterative algorithm, which makes use of a quantum circuit followed by a possibly classical algorithm to find the solution. So what? Okay, so what's the algorithm? Here, we got no code, right? No. I like the other Wikipedia pages because they were pretty schematic, and this seems to be a bit more math heavy. In this section, each part of Simon's algorithm is explained in detail. Yeah. So input. So we get starts with 0. Okay, so we have 2 registers though. Is a quantum state with n zeros. That's a product apply example. So for yeah, okay. First Hadamard transformation. After that, the input as described in the previous subsection is transformed using Hadamard transform, specifically the Hadamard transform. Okay, that's that's this, right? Yeah. So we got an example. So if we now apply Hadamard to the stage, we obtain the following final composite, etc. Okay, so I'm interested in what does the oracle do, because so far then this is the okay, and that's probably the output register, and that's the input register. I'm kind of guessing. Does this have to scroll with me? Where was I? Oracle. When we then call the oracle or black box to compute the function f on this transformed input to obtain the state. Yeah, so the f is applied at the input. Okay. Yeah, but this is still, how is then the function computed? It's really not specified in here, right? Okay, but we get I'm assuming we get a superposition of all the outputs. I think that's what matters, right? I mean, you've got basically fx, so I would strictly read that as first you have, let's take that. So first you've got that superposition, and then you end up with that superposition. Second Hadamard transformation. Okay, so but then that's okay. So you end up basically with your function result in that register. Now, question is, what is this register? Is the top register or the bottom register? Because that's important, right? Because because then it depends where the Hadamard is applied, and that's important to understand the next step. Because this could just as well be that that here you've got the fx, and then here you've got x, right? Whereas you get in here, and that's kind of the superposition here. And then what's happening, because otherwise it wouldn't make any sense. Because you would assume that it's just kind of like that, and there's no if there's no interaction, then this thing is not, then these registers not needed at all. And then pay attention, we measure both of them, so that's also interesting. So how do I figure this out? So let's see. What was the example? Okay, so that's the you see. So that's okay. So we apply Hadamard to the first n qubits, but only so. Okay, so this is the. I assume this is the top. I would call it register 0, and this is register 1, and this is here. This would be the register 0, and this would be the register 1. So we apply so the first one is the register 0. So if they've been consistent with the what am I doing? If they've been consistent with the notation, then right, then yeah. So here we can see this as well. Oh no. Huh. Wait a second. Am I understanding this correctly? X. Yeah, so, okay, so that's register 0. Okay, so the register 0, register 1, register 0, register 1. So you end up with simply, oh no, okay, so you end up simply with fx in here, and here's x. And then you only apply here the Hadamard gate. Mm-hmm. And then you measure both. That's the measurement gate, people. Okay. Okay, so here with the solution space. Okay. So then applied Hadamard transform to the states to obtain. What are you obtaining when you do that? Because I'm assuming that's not really x in here. Oh yeah, it's x. Then apply Hadamard transform to the states of the first n qubits to obtain this state. It can be either -1 or 1 depending on. Okay. Okay, so it's similar. It's similar probably to what happens. It's similar probably to what happens in the Bernstein case, where there's a bunch of control nodes, and that basically shifts, or there's a bit of that definitely shifts. But there's in here, there's no phase kickback, is there? Well, unless there are control sets in there, it could be phase kickbacks. Depends on how you implement that. That's why I like to see an implementation of U, so I could really kind of make a good reasoning about it. For example, if x equals 101, then which is an even number, thus intuition behind this inverse Hadamard transformation that is applied here can be found. So let me just open that on the side tab for a second. I'll take a look at it. Lecture 11. Take a look later. Let's now rewrite these. So measurement, after having performed all the previously described operations, at the end of the circuit, the measurement is performed. There are now two possible cases we need to consider separately. This equals 0 or this equals S, where S is non-zero. First case, let's just analyze the special case 0, which means that f is by requirement a one-to-one function. So that's when this is simply uniformly distributed n-bit string. Oh yeah, okay. That's why it appears 0, right? Because it's a constant. It's like, okay, so it's distributed. It's always the same. Second case, when s is not 0, odd number I have destructive interference. Here's a case where there's constructive interference. Is an odd number. In that case, probability of y is 0, then we never have this case. That is, no string is seen. If the measurement in this case, this is destructive interference. An even number. So, in summary, for the second case, we have the following probabilities. If y times s is even, y times s is odd, classical post-processing. When we run the circuit, resolve, there are two cases. In the special case where we get a 0, in the case where we get non-zero, okay, then in both cases, measurement results in some string y that satisfies that s times y equals 0. Is this another reference to the line s? Then says yes, provided that the process above is repeated several times and a small probability of failure is accepted, especially if the above process runs n minus 1 times, then we get strings y sub 1, y2, and yn minus 1, such that is system occasions. Okay. Not sure I fully grasped that. Not sure I fully grasped that. So, the high level behind Simon's algorithm is to probe quantum circuit enough times to find n bit n to minus 1 as n minus 1 n bit strings, that is such that the following equations are satisfied. But why? I don't know where to even look at. Why is that? So is the model dot spread, that is so and unknowns. Yeah, sure, but why is that? How is that translated to this problem? So you're trying to find a NAS. You're trying to find a NAS that when you add it to X, it gives you the same input, the same output. Why? Okay, let me reread that. Is that all zeros or S? In the case in the cases where s equals 0, then the f is required to be a 1-to-1 function. Otherwise, it's a 2-to-1 function. That is two inputs mapped to the same output. Note that, yeah, so what it means is the case where s is 0 is for the function that it's has like what am I doing? This exactly. No. The input strings 0, 0 and 1, and 1, 0, 0 are both mapped by f to the same output string 0, 0, 0. Oh yeah. Oh, wait a second, but why is, so in this case, S, the solution is 110. It can easily be found that every output of F occurs twice. Oh yeah, but that's weird. And the two input strings corresponding to any given output have bitwise X or 110. For example, the input strings 101 and 010 and 100 are both mapped by F to the same output string 0. If X or within S. And here, oh, so it's not phase estimation. Oh, okay, so basically, okay, that's an XOR. Okay. The other two equal values where this, so if we, this and this, if we XOR that, we get 110. Yeah, okay, okay. So basically, the problem is to find that S. Okay, then when you do the XOR, then the function evaluates to the same. Okay. But still. Yes, it's the probe quantum circuit. I still don't get how they move from that part to that part. Is the modulo 2 dot product that is OI1. Yeah. Yeah. So input since So basically it's about finding that is so you've got basically fx in here. But I don't quite get what happens in the black box. I think it's not really written, because you just do that. So here, mathematically, you just say, okay, so now you got that. And when we applied Hawaiian transform to the states of the first n qubits, then you get that. Which is an even number. Okay, yeah, the minus 1 or 1, sure. Which means the inverse Howard transformation that is applied here can be found here. Putting some can easily convert to a quantum circuit that implements F or classical inputs, class accepts superpositions. X. Okay. Signs omitted, standard practice. For register, output register. Okay. So bitwise X over. And say those references, keep writing them. The sign implementation trick only for. This is a trick that isn't essential, and in some ways I feel bad about forcing you to remember another trick, but it's just so convenient sometimes. Okay, so that's what I just. Okay, so that's what I said. Put in B0. Okay. P1. And what is these? And then bitwise XOR. Okay, that's what I was. That's not exactly what I was saying. But if that's the way it's implemented, B is minus, then either minus if fx is 0. Okay. The computation is effective in the phase sign. Okay, let's see what's now. Okay, it's not a useful example for us. Power of quantum, complex propositions. We can't just look at the state to learn these four answers. This is familiar, critical. No. Rotate, compute, rotate. Further Simon's-Mann triad. Interesting. That's an interesting comment. That Hadamard is a Hadamard transform. It's sort of a Boolean Fourier transform. Sign cancellation. Lots of differences by credit simple state due to pattern in the answers. Okay. And thank God. Okay. I'm not sure if that was helpful totally, but it seems to be a similar, I'd indicate a similar concept. Again, I don't know. It's probably already 40 minutes in the video, or half an hour. So I know that there's okay. So this is where I stopped. So okay. So this is the last time I said this. I know there's fx in the second register and x in the top register. I feel like I really need to take a look at the actual box, for me to explain that intuitively. Otherwise, it's just a mathematical proof, which is what I want to avoid going through in these videos. But basically, that's when you then apply the Hadamard on the top, on the first, right, on the register 0, then is where things get messy, right? Why there's then suddenly this y in here? This literally indicates that the phase that something's happening, the phases in between. I guess it's because again you're using control knots to implement the box and or control knots. And so this in this case intuition behind this guy. Now let's rewrite as follows. Measurement. After performing all previously described operations in the end of the circuit, measurements performed. There are now two possible cases need to consider separately. Can I find an example of Simon's quantum example? I remember I used I used that one. I didn't want to go back to the same thing, but maybe it's. I remember that I went through these the other time. But I don't remember though that this looked this way. I think it seemed to be different. Oh, come on. I just hate that, right? Because, I mean, the quantum circuit there was different. Simon's algorithm. Because the function fulfills the following condition. Yeah. Exclusive. That's an exclusive OR. Okay. Yeah. So this fulfills this example, this requirement, right? So with A being 0, 1, 1. So what do they do in here? So you've got Hadamard's, and then you've got so you apply the first 3 qubits from a register to store X, and the 3 to restore the FX. So that follows the same as in the Wikipedia. Okay, so they apply Hadamard only on the first 3 qubits. That's why you get that superposition. Okay. We apply a controlled NOT U gate with the first 3 qubits as controls and last 3 qubits as targets. You get, for example, the qubits are transformed. Yeah, okay, so this is literally a controlled version of that function. So you're just, okay, putting that into... Okay, and that possible outputs, second register, yeah. Let's measure the second register. Say our measurement is 110. Then you're left with this in there. So with this measure, the superposition of the first register becomes, so that kind of basically collapses the first superposition in the first register, in the register 0 in my case. Time to apply 3 Hadamard gates again. Bitwise modulo 2. Below understand how the first qubit is transformed into Hadamard gates. So you do that. So we make a measurement. So that was okay. So basically what you're showing here is that you're in one superposition you encode the input, another superposition you encode the output, and they are entangled in the sense that you then you got the inputs and the outputs put up these ways, and then if you competitively measure the outcome. But boy, that's not even in the circuit. Let's measure the second register. Say our measurement is 110, right? So you've got 10, 100, and 111 as possible as superposition in the first register. Mm. Mm. Oh my god. Yeah, because of that, the sign is different. Because you've measured, because you've collapsed the output, because you have collapsed the output register. Uh, the amplitude has changed. Yeah. Repeat the gates 2 more times. The second gate and the third gate, and so you end up. So some things cancel out and whatever, and then you end up with this. Before applying the Hadamard gates, both the superposition is this. After applying the Hadamard gates, then you get basically this. Zero, 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 1, 1, 1, 0, 0, 1, 1, 1. So if you go back, this. Okay. After applying the Hadamard gates, we make a measurement. This measurement Z will fulfill the relation below. Why? Give me a second. Freaking soft, and the solution for is either this or this. We know A equals 0 is not the solution, therefore it's this one. Here's the quantum circle we get. Let's work out the math a little more to show. After the oracle function, the two registers become this thing here. Next we measure the second register. Yeah, but where's that thing here? The measurement is here after you've done the Hadamard already. That's what confuses me. And the first register becomes this. Because the equations below come from another source, the equations below use a slightly different notation. In particular, y is actually the z before, and z is actually x. And recall the results in the Hadamard gates. Not happy. Not happy. Okay, but it shouldn't matter in the sense that we can also just we can also just do that, and then based on what we, so after doing that, you've also kind of, because you've applied this function in here. Oh my god, what am I doing? Because you've applied that thing, right? That piece here. So it doesn't matter if you now apply Hadamard over here in that register, right? You're also kind of collapsing part of your superposition, right? Because there's going to be some destructive interference. And so you're going to end up with a reduced space of your kind of like input and output thingy. And then you measure everything. But I don't quite get the relationship. So the equation thing. So if I go back to the Wikipedia page. Here's no fucking Hadamard. Freaking Hadamard's not here. But I guess it's kind of here. I guess that would then be Hadamard and then UF, I guess. Because it doesn't make any sense otherwise. But I hate that. It just makes it difficult to learn, to kind of go through things when you've got sort of different explanations in different spots. But basically, that's kind of where we are in here. Is superposition. Oh yeah, but it's kind of denoted in here that there's superposition, right? So that output register must also be in superposition. So that happens inside the black box, I guess. So and then you perform, but then here they talk first about performing a second Hadamard transformation only in the first register. Which basically, oh man, that feels just harder than it should be. Maybe just because I'm not paying attention enough. I'm just like floating around the sort of intuition level. And I don't know. I need to go drive a little bit around, see if I get sort of an aha moment again. Gonna give you 5 more minutes. Can be 0, so. Basically, you're gonna have so in the most naive of the implementations, right? You would, in the most naive of the implementations, right? The way you would encode that function is is by kind of putting masks all the time, right? In the sense that, like, for that x, right, you want that value. So you would say, if you've got your qubits in here, you would say, you know, you would put an x in here. So you would basically put an x gate in here, and then simply have your control knots or not. You would actually say, if you've got your input and output in here, you'd kind of say, and they're all in superposition, right? So we've got like the Hadamard's here and here. And then you kind of say, okay, for the first entry, I'm just gonna say, so if it's 0, 0, 0, so I need to have negate everything. Then I'm gonna do a control knot in here. And a control knot in here. And this one I'm gonna leave blank. Correct? But then I kind of have to correct that again back to 0, right? And then say, good, so that's the first one. And then if it's 0, 0, 1, so like that. I'm messing up. Oh, am I so stupid, seriously? Dyslexia or something. Ugh. So let's start. This is easier for me mentally to start. So if it's 1, 1, 1, so then you just want this one to be like that, and then that's then if it's 1, 1, 0, right? Oh, sorry, no, that's just, oh my god, that's just, what am I doing? So let's just use Toffoli gates here. Exactly. I'm just plain stupid. So if it's 0, 0, 0, then you want it's not even a Toffoli gate, it's more than that. You want to kind of basically do like that. Assuming that's probably not the way it's done either, because you've got a superposition in here. That's at least what the Medium article says. I don't know. How is this box implemented? Kind of a bit lost. Because if I know how the box is implemented, then I basically can reason about the circuit in a better way, because then I can see the effects of that. But then how do I implement that function in the circuit in a way that you've got, you end up with that particular superposition of inputs and outputs? Mm, 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 mm. In the most naive way, I'm thinking just like, you would hard code those values. Uh, hmm. Two different inputs, we obtain the same output in the case. Maybe this is really the tree. Maybe this is really all what it's all about. That you create interference to create that kind of relationship, and maybe that's the point. And then with one run, you get the x and the fx, and then so you just sample, right? So you do multiple runs to get pairs of those. I guess that's the idea. Okay. I guess that's the idea. But I'll explore that. I'll see. I don't know. I have to think a little bit about it. I have to. I'm almost there. I feel. I'm running out of time for the video today. So, but I think that's kind of the gist of it. Is that you create. So you kind of know the rules. So you can probably you can probably kind of create a function, create a quantum circuit, implement it in such a way that using interference, you're eliminating the. So you're actually creating that type of function. So that you can kind of measure everything. So you've got superposition that is basically that, right? And then so if you just sample that superposition, then then at some point then you're gonna get a north. And three. Then you're gonna get enough strings that then you're able to solve that equation and actually find the answer. I think that's the idea, because classically you need to pick one x, right, and then kind of go through all the values to find another x that equals to this one. But maybe it is not, so you need to find then another one, and then so that's why they say that's kind of the complexity. Okay. I think I'm to the right track, but I'm intuitively that's that's the thing. What's this whole thing about is I'm gonna have to do a recap on all of those. Maybe make a video on all those three, because they all seem to operate in the same, in a similar, and they seem to kind of showcase a lot of those quantum things. Really good for intuition, but it's easy to get lost in them. It just feels a bit awkward the way this is painted in here. That you're doing, it's not really exactly because you need to do that second Hadamard in here. You have to create the interference basically. So what you end up in here is with your actual input superposition of the ones that you really care about, right? I think that's the idea basically. I have to think about it. Yeah, but again, the story repeats itself.